longer because I'm going to go through and fully explain it. But here's what we got. So a particle's position is modeled by P of t, which is sine squared and cosine plus cosine. And then this notation is the exact same thing as saying that x is in between 0 and pi. And they're hard brackets, so 0 and pi are included. So if I have to write the particle's velocity, what we want to do is we want to kind of make a note, well, how does the velocity relate to the equation? So it's always a good idea, if they give you a function in terms of P of t, you should write, well, what is P of t, or what is the velocity related to? The velocity is the derivative of P of t. So we're taking the derivative here. Keep in mind, this squared is the same thing as moving it out here. So that's a little chain rule there. We're going to take the derivative of the outside. And technically there's the 1 here. And then we're going to multiply by the derivative of the inside, which the derivative of sine is cosine. So there's the derivative of the first part with the chain rule. And then I've got the derivative of cosine, which is negative sine of t. So there it is. That's my equation. That's the first part. And you would probably get 1 point for this if it was on a free response question. Most of our work is going to be in problem 2. It says, when does, or at what time, or we could say, when does the particle have a maximum and minimum value for its position? Well, this is where we need to take, and we need to set the derivative equal to 0. Now, since I already defined v of t as p prime, I don't have to write p prime again. Once I write it once, the reader will follow through with the rest of our logic. But you should indicate that when we have maxes and mins, that's when you have horizontal tangents, or when your derivative is equal to 0. So I'm going to take the derivative, I'm going to set it equal to 0, but before I do that, you notice it has 2 parts to it. And each part has a sign in common. So I'm going to actually factor out a sign from each piece. And you can do that. It's just reducing one step. And then I'm going to use the zero product property. And we're going to set each individual parentheses equal to its own 0, and then we're going to solve. Now, you might, excuse me, you might have to review your trig here. I'm hoping this is really kind of something you can do fairly quickly. When is sine equal to 0? Well, we got to think about sine is the y value, and of all these points, when is the y value equal to 0? Now notice we're going from 0 to pi. So 0 and pi, sine is equal to 0 at both of those spots. So when does the sine value equal 0? At 0 and at pi. We actually have 2 answers here. You don't need to show any work for this problem. It's basically, they're saying that you should have this memorized from the unit circle or knowing your quadrantial angles there. But this one might require a little bit of work. I need to get cosine by itself. So I'm going to subtract 1, divide by 2. And now this is where, if you mastered the unit circle, you know this answer. And I always just say, I haven't, but I've mastered SOHCAHTOA. And I know that cosine is adjacent over hypotenuse. So I'm basically going to see when do I have an adjacent of 1? Now adjacent is always moving left or right. So when is my adjacent 1 and my hypotenuse is 2? Well, this is a special kind of triangle. 1, 2, square root 3 is my special 30, 60, 90. And again, you may have a different way of doing this, but across from the square root of 3 is always 60 degrees, but my answer is in radians. So I can't say the answer is 60. I have to convert 60 into radians, and that's pi over. So that's the first answer, but there is a second answer. The second answer has the exact same setup except for reflected down. My hypotenuse will always be positive, but now it's a negative square root 3, but that still keeps this adjacent side of 1. So I still have 60 degrees, but if I go and I want to keep this between 0 and pi, notice this goes from 0 to pi. I don't have another answer in this quadrant. This is actually, and it's not part of my answer, but if I went all the way around at 2 pi, that would be 6 pi over 5 or over 3. But I didn't go all the way around. I actually went a third less than that. So I went 5/3, but 5/3 is not in the interval from 0 to pi. So I'm not going to include that answer because it's not in the interval, which means I have 3 critical points. Right? Those 3 points are when the particle is, actually we could probably answer it right here. It's when the particle stopped, right? Because that's when the derivative is equal to 0. Well, we'll do that in the next problem. So what are we going to do? We're going to make our sign chart. I'm going to take P of t, and we've got 0, we've got pi, and we've got pi over 3. And actually, you know what you could do here is you don't even need this sign chart if you're just finding max and mins, because it doesn't, you could just go ahead and make a regular table, but I like reviewing the sign chart. Now what I'm going to check here is the sign between all these points, but notice my interval goes from 0 to pi over, to pi. Oops, this should be flipped around. I didn't realize that. Pi over 3 is in between pi. Again, there we go. Pi over 3 and then pi. These should go numerically increasing from left to right. So I'm going to check signs in between these values. Now notice, I don't have to check this value here because my interval starts at 0, and I don't have to check anything to the left of that either, but I will have to find the values at some point of the endpoints. So I'm just checking the points in between. Well, what point is easily in between 0 and pi over 3? That's pi over 4. And then what point is in between pi and pi over 3? That's pi over 2. I'm picking the easiest values that I know to test. And then we're going to go back to the derivative. I would suggest taking the most factored form, because that's probably the easiest. And pi over 2 is probably the easiest to evaluate. So if I go to pi over 2, I'm thinking, just since I have this here, what is pi over 2 at sine and cosine? Well, that's going over 0 up 1. So if I test pi over 2 and I plug it in here, sine of pi over 2 is 1, and cosine of pi over 2 is 0, so this becomes 0 minus 1 or negative 1. So 1 times negative 1 ends up a negative value. And then pi over 4. Now this one might require a little bit of work, but you might think of this. I'm going to probably end up erasing this, but if I go pi over 4, right, that's 45 degrees. That's 1, 1, square root 2. Notice they're all positive. So if I plug in pi over 4, sine of pi over 4 is positive 1 over square root 2. I don't care about the number, I just know it's going to be positive. If I plug in cosine, cosine is going to be 2 times, so if I plug in 2, cosine of pi over 2 is 1 over square root 2, or if we simplify that, we end up with the square root of 2 minus 1. Well, the square root of 2 is bigger than 1, so this is positive as well. So, like I said, you may have to review your trig a little bit to solve those, but that should be something that should be very kind of straightforward. All right, so what do we got? I need to identify, well, what's happening here? I go from increasing to decreasing slopes, which means I definitely have a maximum at pi over 3. But then I don't know about the endpoints, right? What's happening at 0 and what's happening at pi? I didn't check the endpoints or the signs because we don't need them, but I should make a quick little table to determine what are the values of the original function, and that's the key. Sign chart can tell us where max and mins occur, but if I actually want to know what they are, we got to go back to the original function, 0. We might as well figure out pi over 3 and pi. So I'm going back to the original function to test these points, and if I plug in 0, zero should be really friendly. We already know what sine and cosine are. So sine is 0, 0 squared is 0, cosine of 0 is 1, so p of 0 is 1. And let's do pi, since that's the easiest one, the next easiest one. And you don't need to show this work. I'm just kind of showing you I'm using the original function. Oops. And I'm going to plug in pi this time. And we notice at pi, sine is 0 and cosine is -1. So this whole piece will be 0, and this will be -1. That means the only thing I have to do is then calculate pi over 3. And this might require a little bit more work. If you don't know your unit circle, then you're going to have to know what is cosine at pi over 3 and what is sine at pi over 3. Well, notice we already set this up, right? You actually kind of already know what it is, but let's just double check. If I look at cosine, cosine is hypotenuse over, or excuse me, adjacent over hypotenuse. And pi over 3 is the same as 60 degrees, so if I use the green triangle here, I get 1 over 2, or 1/2. So that part's 1/2. And then what is sine? Sine is square root 3 over 2. So I get square root of 3 over 2, and then remember that's squared because it's sine squared, plus 1/2. So square root 3 over 2 squared ends up being 3/4 plus 1/2, but instead of writing 1/2 as 1 over 2, I'm going to write it as 2 over 4, so I can add my fractions together. So now we officially can determine what's happening at each point. And because this is a continuous function, I basically start at 0, and then I increase because I have a positive slope. So this would be a minimum. We already know that this is a max, but now we just prove that 5/4 is the largest number. So that's the absolute max. And then we're decreasing past that minimum. We know the slope, so it's decreasing all the way until I get to -1, which makes this a minimum. And actually, of everything on here, it's the lowest point, so that's the absolute minimum. Okay. Now, some of you might be saying, Strab, I can do all this on a graph without showing any calculus. And I'll say, cool, but you're not going to get any points for it, right? You have to show the calculus. Just to show you, I took the original function in Desmos, and I put the domain from 0 to pi, and here's my graph. At 0, we had 1. At pi over 3, we had the maximum, and then right here at pi, we have the minimum. And then you can see the function has positive slopes and then negative slopes. Okay, so that's just a graphical confirmation of that. All right, this was the all the work we needed, because now we can answer part 3 quite quickly. When is this particle stopped? Well, you should indicate how you know that. It stopped when the velocity is equal to 0, and we just found those points, right? When are they equal to 0? Okay, somebody just asked why 1 is not a maximum. I'm assuming that's the output 1. If I go over 0, up 1, notice of all the points around it, it's the lowest near it. And the reason why we knew that is because my slopes were positive. So if you look at this sign chart, see how it's positive going from 0 to pi over 3? That means the function is increasing, so 0 had to be a lower spot than pi over 3. And all the points between 0 and pi over 3, 0 is going to be the lowest because my slopes are going up. So that's why this was a minimum here and not a maximum. Okay, so where are when's the particle stopped? Those are my critical points. So we know the answer is at 0, at pi, and at pi over 3. And those are the official spots where the derivative is equal to 0. Now this is all the justification you need right here. That's it. Okay, when are you moving forward? Well, you're moving forward when the derivative is greater than 0. So that's why we had to do the sign chart, is we are moving forward between the spot of 0 to pi over 3 because I have positive slopes. And then when are you moving backwards? Whenever you have the negative slope. So you don't have to write a lot of words for the justification. You just have to tell me how you know that. And it's all based off of the derivative. Okay, so that was this problem. Okay, so if we look at the two problems, they actually have the exact same endpoints. So really, we only have to do this problem once. And we're going to look at what is the average rate of change. Well, visually, that is the slope of the secant line that connects the two endpoints. And if I just kind of estimate that in here, we're just looking for average rate of change is just your slope. So whenever you see that, it's your change in y's over your change in x's. Now I could have wrote x2 minus x1 over y, or y2 minus y1 over x2 minus x1. I could have wrote the slope formula in terms of x's and y's, but it's better to think of it as if I have a point A, then its output is f of A. If I have a point B, then its output is f of B. So the average rate of change is your difference in your y or x's on the bottom, so 4 minus 1, over the difference of your y's up top. So we end up with 3 over 3, which is equal to 1. Now, that is the exact same work as down here. But we're not just testing slope today. We're testing our understanding of what slope is. And here's the question of the day. All right, is there a point where the tangent line is parallel to the average rate of change line? So is there another point on this graph where if I take this and clone it, and I want to be tangent, which means I have to touch this function at one exact point, and right there. So if I look at this, this is an estimate, but this is the tangent line. Right? And if I kind of estimate this, yeah, there's a point roughly at x equals 2.1 maybe. We don't know. We're going to actually be able to find out how and exactly why that is, what it is. But you can see, what does this show? Well, let me rewrite this. This red line on the bottom shows the average rate of change that has a slope of 1. And this line up top is a tangent line which shows the derivative at some point C is equal to 1. So, and that's the idea here. Actually, instead of saying 2.1, I'm going to say x equals C. Okay? Now let's look at this example down here. We have to be super careful with this problem. Does this graph have a point of tangency where the slope is exactly the same as the average rate of change? And if a lot of kids are going to be like, oh yeah, right here. Well, we got to be careful because this could be a pivot point, right? It doesn't guarantee, because doesn't that look tangent as well? And these lines aren't parallel. So what happens here is there is officially no point right here, and the reason why is this is non-differentiable. We studied that word back in trimester 1. It means the derivative does not exist. Why? Because this is kind of like a cusp, or some people could say even a corner, but the slope on the left is positive, the slope on the right is negative, so this point can never be equal. But if we look up here, the point on the left and the point on the right, those derivatives are equal. So what this actually shows us is a visualization of the mean value theorem. If the function is on a closed interval and it's continuous and differentiable on the open interval, then there always will exist a point that looks like this, where the average rate of change is equal to the slope of the tangent line. But if the function is not differentiable, then there is not guaranteed a point to be parallel. Okay, so this is going to be an existence theorem. I want to show you this visual quick. So again, don't write this, but we're going to basically look at the same thing. And what I want you to be aware of is the conditions that work versus the conditions that don't work. So let's say I have an average rate of change that goes from 5 to wherever this point is 0 in the y values, right? Or I go from 0 to 8.5. Is there another point on this line, or maybe there's more, where the slope, the average rate of change is equal to the slope of the tangent line? And look at right here. Right there at this point, this tangent line is parallel to the average rate of change line. And there's another one right up here. So actually, I've got 2 points. Right here, we could call this C, and we could call this point D, somewhere down here. But there are 2 lines where the derivative of D and the derivative of C is equal to the average rate of change. Okay. Now, what if I did the same thing with this one? And this time, what if I go from 0 or from 1? Actually, you know what? Let's go from 1 to 5. So if I just look at it from 1 to 5, notice there is no perfect point because the point of tangency would occur at a cusp. So in this case, we cannot conclude that this slope is equal, and the reason why is this is non-differentiable because it's a cusp. All right, so I don't know why these were doubled up. Let's just look at this last one. What if I try to go between the points of let's say this endpoint right here and this endpoint right here. So 0 and 9. Is there another point of tangency on here between that full interval where these are equal? Well, now notice there actually appears to be 2. right? There appears to be a point of tangency here and here. Now notice, just because I say tangency doesn't mean like it should touch the graph at one point. So here's the tangency point. That means we would kind of not focus our line any further. Doesn't have, even though it goes through here, that's still tangent to this point. However, we have a big problem here. This point is on a function that is not continuous. And if you have a non-continuous point, we cannot guarantee that these tangent lines do or do not exist. Now, graphically, we saw that, but right here, this graph is non-differentiable. And the reason why is because it's discontinuous. So you got to think about what we know about the differentiability pieces. So it's discontinuous. If it's a cusp, a corner, even if there's a vertical tangent, that means that it's non-differentiable there. So therefore, when we learn about this mean value theorem, we have to check different pieces. And here are the steps. Now, Mr. Waffler already described the mean value theorem in the video. I'm going to do that briefly on the next slide. But what he didn't do is put down these steps here. Okay? So I would write this down if I were you. How do we apply the mean value theorem? Well, mean is really just referring to the word average, right? So think of that, the average value theorem. That's what we're testing is if we know the average value, does that average value match the derivative? So there's 4 steps. The first 2 are confirmation pieces. You have to state that these 2 pieces exist. So you have to determine if the function given is continuous, and you have to say it is. You also have to determine that it is differentiable. And you need to state those. If you don't state those, then you're not stating the hypothesis of the mean value theorem. And then we got to calculate average rate of change, which we've already done that. That's just slope. And then we compare the average rate of change to the derivative. Once you get the hang of it, it's actually a pretty friendly process if you remember these 4 steps. See how it works. This is the official theorem. Now notice how it's stated. If then, we're going back to geometry. If the hypothesis is true. So your 4 steps that you had to do, well, here's the first 2 steps in the hypothesis. If f of x is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, then there exists at least one point x where the instantaneous rate of change is equal to the average rate of change. Or another way to say instantaneous rate of change is the derivative. The derivative is equal to the average rate of change. So this is the work we're going to be doing, and you know how to find slope. You also know how to find derivative, so we're just comparing the derivative to the slope. And then we're going to solve using algebra. Okay, I'm going to show you another graphical visualization here, just so you can see it, but you don't have to write the graph part down. All right, so if I take my green line, that's my average rate of change between points A and point B. Now notice, if the output for A and the output for B are the same, then your slope is going to be 0. And what we're actually looking for is, are there any other points between A and B on this graph that is the slope is equal to 0? Well, you should be able to identify it very quickly. But notice I want to check. F is continuous from A to B on the closed interval, and then it's differentiable. There's no corner, cusp, or vertical tangent, so we're okay. Well, now, if I just move this line up, you can see there's one point of tangency. Maybe I make this line a little bit smaller because we're only concerned about the tangent line at that point. But then there's another one down here, and there's another one down here. So there are 3 points on this graph where the slope, the average rate of change, is equal to the instantaneous rate of change. And because I don't know what these values are, I'm just going to call them f prime of x, even though there would be a c value that we would find, the actual location. All right, so let's look at just another quick graph here. If I do this one, and I go between the 2 points, so I'm just matching up the outputs from A to B, and we want to see, okay, how many tangent lines are there that are parallel to this average rate of change. So what I'm going to do is just kind of copy that average rate of change. If I copy it, it's the same slope. Well, then you can see I've got a point right here. You can see that I've got another point right there, and then we're only concerned about the points from A to B, so this one past it is not on that interval from A to B. But A is continuous and differentiable. There's no corner cusps on here or discontinuity that's going to break it up. And I may leave this red one right there. It looks like there might be another point. But there's 1, 2, 3, 4 spots between the interval and A and B where the average rate of change is equal to the derivative, or the instantaneous rate of change. Well, here's what I'd want to do. We want to find the C value that satisfies the mean value theorem. Well, the first thing we have to do is you have to state f of x is continuous. You don't have to explain why you know it's continuous, but it's continuous on the closed interval. Okay? We know this is true because this is a polynomial. Okay? Then you have to state that f of x is differentiable. On the open interval. The reason why it's open instead of closed is because at these two endpoints, the derivative to the left or the right don't exist. So that's why we have to have open symbols. But this is the first part. You have to state this. If you don't, you're not stating the if portion of the hypothesis of the mean value theorem. When you use theorems, you have to state the hypothesis. All right, so there's the first part. And then the second part, I kind of think of this as side work almost, but the second part, we're then comparing how does the derivative at C equal to the average rate of change. So this is the conclusion part of the mean value theorem. Well, I need to know what's the derivative at C. I need to know what is f of B and f of A. Yes, we have a graph, so we could get that from the graph, but let's pretend we didn't have that graph. I think of this as side work. Okay? I need to find the derivative at C. Well, the derivative is very friendly. So we're just going to take the derivative of the function, but then I want it to be at the value C, so we're just going to call it C instead of X. Now I will note, you do not have to show this side work. If you can do this part in your head and you know what that's going to look like, okay? So we just took the derivative, put in C, and then that's going to equal to the interval from A to B. Well, all right, B is 4, A is 0, and then I have to find their outputs. So That's the other work that, again, you don't have to show any of this work for the side work. I'm just showing it to you so you guys can get an idea of how we're getting these answers. Well, f of 0 is equal to 1. And then let's plug in 4. So 16 minus 12 is 4. 4 plus 1 is 5. So it's just like we're finding the slope. F of b, so what is the output when x is 4? What is the output when x is 0? So notice, what did we do? The blue part is the average rate of change. That's going to be the slope between this line. And that's pretty quick. We get 4 over 4, which is equal to 1. So the slope between the two endpoints is 1. Now graphically, if I was to draw this perfectly, where else is my slope equal to 1? I'm guessing here, but this is the derivative at, I'm going to put 2 for right now. I might change it depending on what my answer is. But I need to know these lines are parallel. So if that slope is 1, this slope is 1. And then that's the work that we need to do, is just find the C value. Now the algebra is going to get harder, but again, we're starting off with a faster, easier example so you guys can get used to it. So now we want to solve for C. Add 3, divide by 2, and there it is. So even my graph estimation is right on. Okay, again, we should have done all this without the graph, right? We know how to find the derivative. We know how to find both outputs. Take the slope, the average rate of change, and set it equal to the derivative at C, and then you're going to solve. So how is it going to get harder? Well, the only way this gets more challenging is the derivative is going to get more difficult, and then the algebra here gets more challenging. Okay, so if I'm doing this problem and I know for sure that I have to use the mean value theorem, the very first thing I'm going to state is my if, the hypothesis. So before I do any work or anything, I'm going to just say, what do I know? F of x is continuous on the closed interval from pi over 2 to pi. Why do I know that? Well, let's think of this. The function x is just a straight continuous line. You can think of that as a polynomial. The function cosine is also, cosine just goes like that. So cosine times x are two functions that are always continuous. And when they multiply together, they will continue to be continuous. And there's no breaks or jumps or any weird parts about this. So that also means that f of x is differentiable. On the open interval. All right, so those are the two things you have to write. Now you might be thinking, Strab, I don't know if I trust you on that. Let's check. I just graphed this, even though eventually you're going to do this without a graph. Let me just show you what this graph looks like. So this is the graph of x times cosine of 2x. But we have a restriction on it. We have it from pi over 2 to pi. So here's my graph. Now, if I was to take this graph and draw a line from here, from this endpoint to this endpoint, you could see the average rate of change, and you can probably guess that there's going to be a parallel line to this tangent here, and another one somewhere close to here. So my answers are going to be just over 2 and just below 3. What I'm going to do is take a little screenshot of this because we're going to need it later on. And I'll apply that in a second. Okay, so once we confirm that we can use the mean value theorem, then the second thing, and so if you want to do it, this could be step 1, step 2, step 3 is find the derivative at c, and then step 4 is find the average rate of change between the 2 points. It doesn't matter how you number your steps. The side work here is what's important, and actually I want to make this in red. So I need the derivative, and this is a product rule with a chain rule mixed in there. So that's our practice from last trimester. So let's do that. Product rule, here's U, here's V, oops. And I'm going to assume we can do most of this in our head. So the derivative of the first part is 1 times the original second part V plus the original first function times the derivative of the second. Well, the derivative of cosine is negative sine. Keep the inside, but then we have the chain rule. The derivative of the inside brings that 2 out. All right, so there's my product rule. Now I'm going to just rewrite this and simplify a little bit, but instead of saying x, I want that value c to be plugged in there. And this is the part I'm going to simplify. I've got a 2, a negative, and an x, but the x is going to turn into a c, so I'm going to call that negative 2c sine of 2c. There's the derivative at c. And actually, instead of saying plus 2c, I could just say minus 2c. And then I need to find my outputs. I need to find the f of b and f of a. Well, we have a, we have b, so let's just plug those in. And then it's just algebra and a little bit of unit circle. So if I simplify f of pi over 2, well, the 2's are going to reduce out inside, so I'm just looking at cosine of pi. At pi, cosine is negative and sine is 0, so I get negative 1 times pi over 2. So there's my first output. That can be f of a. And then I got to evaluate the next one. The cosine at 2 pi. 2 pi is all the way around the circle. Cosine is your x value at 1. So f of pi is equal to pi. So hopefully this is all pre-calc stuff. You guys are comfortable with that. If not, then that kind of gives you an indication of what you really need to study. b minus a. All right, well, b is pi, a is pi over 2. F of b is pi minus f of a, which is minus pi over 2. And then we just have to solve. Now, and here's the tricky part. Up top, I'm going to write this so it'll be easier to solve. I'm going to change this to 2 pi over 2, and this one to 2 pi over 2, so then I can work with my fractions a little better. And actually, this top part is 2 plus 1 is 3 pi over 2. And on the bottom, I get 2 pi minus 1 pi, so I get pi over 2. But now notice what happens. I've got a number divided, I got a fraction divided by a fraction. So I'm actually going to change this part right here. Instead of dividing by pi over 2, I'm going to times by the reciprocal, which is super friendly because look what happens. The 2's go away. The pi's go away. And you're left with 3. Well, now I have to solve for c, but notice I've got 1, 2, 3 different spots that I have c, and this looks kind of nasty. Which means, and I didn't tell you this at the start, but this is a calculator problem. Because once we get to this point, I'm going to move the 3 over here, and I want to figure out when does this equal 0. So what you could do is you could take this part right here, put it into your calculator. Instead of c, we'll put x. And then we want to figure out where it crosses the zeros at. Mostly because of time, I'm going to use Desmos really quick and just type this in. Desmos is much faster. But you can still do this on your calculator. Okay, and then I'm going to put the same domain because we're really only focusing on these spots. So where are the spots where this green function crosses 0 on this interval? That's right here, 2.078 and 2.964. I'm going to write that over here quick. .078. Okay, so I'm just going to confirm this graphically or geometrically. Oops. So let's look at this, just what did we do? I think it's an important piece to see it visually. I connect the two endpoints of this graph right there. And then I clone this, you can kind of see sorry, I'm just getting my colors straight. All right. So if we look at this, the green line is the average rate of change. And we know that the average rate of change was equal to 3. That's what it all simplified out to be. So your average rate of change is equal to 3. And then I know that the red line right at this point, now notice it's almost at 3. It's just a little bit below 3, which is 2.964. So the derivative is equal to 3 as well, and derivative is slope. And then look at right here, just past 2, barely past 2, the derivative at 2.079, or excuse me, 78, is equal to 3 as well. So the average rate of change is equal to the instantaneous rate of change at those points. Okay. We're not going to have time for this one, but I just want to show you one thing quick. So don't write this, but here's what I'm thinking right away. I see this graph, and it is assumed that you know what this graph looks like. This graph is undefined at x equals 0. But then its graph goes like this. So if I go from 4 to 8, okay, and this is not a perfect sketch. It's not awesome at all, but notice this part of the graph right here is closed and continuous and differentiable. So the mean value theorem applies, and then you just take the derivative, but remember you just have to rewrite it here. So we're not going to do this one because we've done one like this, but that's the derivative. And then I want to show you this part right here. This is a multiple choice question, okay? And it's based off of tables. You will see a lot of questions that are based off of tables on the AP question or on the AP test. So I just want you to be aware. You cannot assume you know what's happening in between these points, right? If I said 6, you don't know if 6 is at 4, or what if 6 is at 400, or what if 6 is at negative 400? We don't know. So you cannot assume anything about a table except for exactly what is written. So let's look at this, and I'm going to have you choose your answer, A through D. But James said that h of 7 minus h of 3, so here's h of 7 is 5, h of 3 is 1, has to equal 1, then there must be an interval from 3 to 7 for which the derivative at c is equal to 1. All right, so if I checked this, and I just put 5 minus 1, well, let's check. 5 minus 1 is 4, 7 minus 3 is 4, and that equals 1. So James said that which conclusion or which condition can James make true? Is it h is continuous over the function? Is it h is continuous and decreasing? Is it h is differentiable over the closed interval? Or is it the derivative as we go to 5 is equal to 1? So which one of those is the only condition that James can make? All right. So the only statement that is going to make James's condition true is if the function is differentiable. Because notice, it doesn't say anything up here that the function is differentiable or continuous. Now, if you just say it's continuous, it also has to be differentiable because this part right here is the mean value theorem. So that's what they want you to see. When you see this, this is the mean value theorem, which means my function has to be closed and continuous. If it just says continuous, this is not officially 100% true. It's not wrong, it's not 100% true. Continuous and decreasing, we don't know if it's decreasing because I don't know what's happening in between, so part B is wrong. And this is saying that the derivative to the left and the derivative to the right is 1. We don't know that. The only thing that would make James's statement true is if he said the function was differentiable. And the question is why? Why? How come it wasn't part A? Differentiability implies continuity. Okay? Continuous does not imply differentiability. So if you see the word differentiable, think it's also continuous. All right, so here's what we got for homework tonight. It's out of our textbook. And I'm going to put a couple of things. Your homework tonight is just these problems up top. However, if you want to start getting prepared and start practicing, you have optional AP review problems on this page. I would recommend doing them. I'm not going to check them. I'm not going to grade them. That is for your own benefit to get practice and well-versed for the AP test. Okay, so that's all I got. I'll be available in my office hours from 1 to 2 today. If anybody has any questions, stop on in.
Mr. Strub, I'm struggling with 5.1. Is there any questions I can do for that?
I would, let's see. So did you do the delta math?
Yes.
Okay. You can always do more problems in delta math if you reopen that up and just keep working through them.
Okay.
Otherwise, if I don't have my book right in front of me, if you stop into my office hours, we could look at like some book work out of 5.1, and I could just sign a couple of problems there and you could work on that.
Okay, sounds good. Thank you.
Yep, no problem. All right, Alyssa, Jeremy, you guys got any questions? If not, I got to jump to my other class here.